The composition of the reaction system is usually known more precisely as that initial state than at subsequent times. This is because composition at later times are generally evaluated from a limited experimental analysis plus assumptions that certain reactions have occurred. For non-elementary reaction, rate constant from data at initial condition may differ from K values obtained at later stage, as explained in section 2.7. By comparing rate constant and reaction order obtained at different extents of reaction, conclusion may be drawn about the reaction mechanism. When the rate equation determined from the concentration dependency at initial condition is different from the determined at finite conversion. Some change arising from the presence of intermediate or stable products is indicated when the order of a reaction determined from data at significant conversion is less than the order at initial condition. The rate is decreasing less rapidly with time than expected. This suggests that the product of the reaction somehow speed up the rate. Such systems are called autocatalytic. Conversely, when the order at significant conversion is greater than that established at initial condition, the products of reaction must inhabit the reaction. This value agrees well with the result 1.7 into 10 to the power inverse 3 obtained by the integration method. Both methods show that the second order mechanism is preferable. However, the failure of the first order assumption is perhaps more clearly shown by the differentiation method than the integration approach. The data in figure 2.5 do not approach a slope of 1.0 at all closely, but the K1 values in table 2.3 are of the same magnitude, differing from an average value by not more than 17%. This is because the integration process tends to mask small variation. Third order reactions are uncommon. Fractional order and rate equation with concentration dependent term in the denominator may occur when the reaction represents a sequence of several elementary steps. Procedures for establishing the order and rate constant for these cases are similar to those already considered. Experimental data that suggest fractional order rate equations should be examined carefully for effect of physical resistance. Sometimes these effects, rather than a sequence of elementary processes, can be responsible for the fractional order. An example is the study of hydrochlorination of royal alcohol with zinc chloride as a homogeneous catalyst. This homogeneous constant volume reaction was carried out by dissolving gaseous HCl in a stirred vessels containing the alcohol. The resulting concentration time data could be correlated with a rate equation half order in alcohol concentration. However, the rate constant was found to vary with the gas HCl flow rate into the reactor, suggesting that the observed rate was influenced by the resistance to diffusion of dissolved HCl in the liquid phase. A method of analysis which took into account the diffusion resistance indicated that the chemical step was probably first order in dissolved HCl and zero order with respect to L'Oreal alcohol. Such combination of intrinsic kinetic and mass transfer are not considered when heterogeneous reactions are discussed. Chapter 10. Concentration versus time equation for reversible reaction. For an elementary process, the ratio of the forward and reverse rate constant is equal to the equilibrium constant. For example, equation 2.15. Hence, the net rate of reaction can be expressed in terms of the forward rate constant K and the equilibrium constant. Then the integrated form of this rate expression can be used with concentration time data to evaluate K. Just as the irreversible reaction, the procedure is illustrated for first and second order rate equation. First order, if K1 and K1 dash are the forward and reverse rate constant for the elementary process, the concentration of B can be expressed in terms of Ca by the mass balance at constant volume, thus volume, and since the number of moles is constant, the concentration of B is its initial value Cbo plus the concentration of A that has reacted, that is combining this result with equation 2.56.